Ladies and gentlemen, welcome back to Group Theory. This course talks about groups. Groups are sets with operations that respect certain properties. In Lesson 9, we're going to be exploring what happens if we take a subset with the same operation and we find out that this subset is in its own right a group. So, the first thing to do is to define what a subgroup is. That is what we call this nice subset that respects the operation. Afterwards, we will give some examples of subgroups and examples of non-subgroups. Later, we will see that there is a very nice criteria that we can use to determine whether a subset is a subgroup or not. Afterwards, we will see that the kernel and the image are subgroups of the sets that they live in. And lastly, we will see that if you take any two subgroups and you have their intersection, we would get another subgroup. So the thing I want to point out is on the right here, this is a graph of a group we've already seen before in lesson 6, which I recommend you check it out. It's called the quaternion group, Q8. And it contains 8 elements, including the identity element, I, J, K, which are each the square root of -1, and their inverses, -I, -J, -K, and -1. So in this large group, we can see that if we take only the elements 1, K, -1, and -K, we get another group with the same operation as that of Q8, which is multiplication. We see that all the conditions of a group, associativity, closed under inverses, closed under the operation, and the identity element, all of these conditions are met with this smaller subset. So we call this subset a subgroup of the quaternion group Q8. So let's get started. The first thing we're going to be looking at is the definition of a subgroup. Definition: let G be a group and H a subset of G. We say H is a subgroup of G, and we denote it by H a subgroup of G if, firstly, H has to be non-empty. If H is an empty set, it is automatically not a subgroup. Secondly, H is closed under the operation of G. This means that, in mathematical terms, for all H1, H2 in H, we have that H1 times H2 is also in H. So all the products of H1 and H2 are in H, no matter what H1 and H2 are. Thirdly, we have that H is closed under inverses, meaning that for all H in H, we have that the inverse of H is also in H. So again, if H is a non-empty subset that is closed under operation and inverses, then H is a subgroup of G. We can say that H is in its own right a group with the operation of G. So it's very important to check that the operation that we use for H is the same one that we use for G. So if G had an additive operation, for example, H should have also an additive operation. It has to be the same sort of operation. Moreover, if H is not equal to G, we call H a proper subgroup because H is strictly contained inside G, as there are elements that are contained in G that are not contained in H. And we call it, in fact, a proper subgroup of G and denoted by H, a proper subgroup of G. Now that we have defined what a subgroup is, we are curious to see what is the identity element of that subgroup as a group. Well, it is not surprising to see that the identity element of H is the same as that of G. And let us prove it. If H is a subgroup of G and H is an element in H, then by one of the properties, we have that the inverse is also in H. So if we take H times H inverse, we would get the identity of G. But H times H inverse, by another property, we know it is inside H because H is a subgroup. So that means that 1G is also inside H. So because the identity is a unique identity, there are no two different identities, we must have that the identity of H is equal to the identity of G. So in any subgroup, we always have the identity of G inside. So since H is non-empty, the least we can have in the subset H is the identity. Let us now look at what could be considered as subgroups and what could not be considered as subgroups. The first example, we have most basically that the integers is a subgroup of the rational numbers, which is a subgroup of the real numbers, which is a subgroup of the complex numbers. Note that it's important to specify the operation here, it's addition. So all of these groups have the same operation in common, which is addition. Secondly, we have that for any group G, the smallest subgroup that there could be inside G is the group containing only the identity in G, since we've already mentioned that for any subgroup H in G, the identity of H should be the identity of G. So this is the smallest subgroup. And the largest subgroup that could be in G is G itself, because we know that G is a group. So it is considered as a subgroup of itself. These are called the trivial subgroups because any group G contains these two subgroups. Thirdly, we have that the multiplicative groups, so the groups with the operation multiplication, we have that minus 1, 1 containing the identity, the multiplicative identity 1, is a subgroup of Q star, all the non-zero rational numbers, which is in turn a subgroup of R star, the non-zero real numbers. We have in number 4 that minus 1, 1 with the operation of multiplication is not a subgroup of the integers with the operation of addition. That is because even though minus 1, 1 are integers, we have that the operation in this group is not the same operation of that group. And we have said that the subgroup and the ambient group should share the same operation. So be careful of that. Now, consider the subset V4 inside the symmetric group S4. If you don't know what a symmetric group is, I highly recommend you go back to lesson 5 in the course to learn a lot about this interesting set of groups. So, the subset V4 in S4 defined as V4 containing 4 elements E, A, B, and AB, where E is the identity permutation, A is the double transposition 1, 2, and 3, 4, and B is another double transposition, which is 1, 3, 2, 4. So naturally, the last double transposition possible would be A times B. So AB would be equal to 1, 4, 2, 3. And so we have ourselves a subgroup. Moreover, notice that V4 is abelian. That is, it's a commutative subgroup. And if we write down the presentation of the group V4, we would say it is generated by A and B, and they have this certain relations that V4 satisfies, which is A squared is equal to the identity, B squared is equal to the identity, and AB squared is equal to the identity. The reason being is that we've seen in lesson 5 that a 2 cycle has order 2. So if you square a 2 cycle, you get back the identity. Since we have both of these cycles here as 2 cycles, squaring them both at the same time yields the identity. So this is why A, B, and AB have order 2. So V4 has a special name and we call it the Klein 4 group. And that is example number 5. The next set of examples will concern the dihedral groups, which we covered in lesson 4, which I also recommend you check it out. For Example 6, we have that in D to N for any dihedral group, we can take the subgroup containing all the multiples of the rotations. So r squared, r cubed, all the way to r to the n minus 1 power. And we know that r to the n is equal to the identity, so it's just going to be a cyclic subgroup of D to n. If you do not know what a cyclic subgroup, stay tuned. This will come in the future videos. So example number 7, we have that z bigger than 0 and with multiplication is not a subgroup of r star with multiplication. The reason being, even though z bigger than 0 is a subset of r star and they have the same operation, however, we have that z bigger than 0 with the dot is not even a group because it is not closed under inverses. So for example, if you have 2 in z bigger than 0, there is no inverse. Usually the multiplicative inverse of 2 is a half, but a half is not inside z. It's not an integer, so it would be in r star instead. So if this is not a group in the first place, then definitely it cannot be a subgroup. It makes sense. Every subgroup is a group in its own right. For number 8, we have that the dihedral group D6, so the dihedral group responsible for the symmetries of a triangle, three-sided polygon, is not a subgroup of the dihedral group D8 responsible for the symmetries of a four-sided polygon or a square. The reason being is that D6 is not even a subset of D8 because there are elements in D6 that are not found in D8. And how is that? Well, if you look at the elements in D6, what do you see? You have rotations and reflections of a triangle, not a square. So if you take a rotation of a triangle, it would be a rotation of 60 degrees. But if you take a rotation of a square, it would be a rotation of 90 degrees. So the r in D6 and the r in D8 are very, very two different r's, not the same element at all. So we might as well say this is r tilde because they are two different rotations. So D6 is not a subset of D8, therefore definitely not a subgroup of D8. For example 9, we have D6 and D12. So D6 concerns the triangle and D12 concerns the hexagon. We know, we can use a similar argument as before to say that D6 is not a subgroup of D12. We can do that and move on to the next example. However, before we do that, notice that if we create an H, which is a subgroup of D12, so if we take the elements in D12, which are 1, r square, r4, s, sr square, and sr4, and we've combined them all in a set we call H, we find quickly that H is a subgroup of D12 using the properties that we mentioned above for a definition. However, D6 and H are two different sets because remember, the rotations in a triangle are not the same as the rotations in a hexagon. However, we can construct an isomorphism between D6 and H, and the isomorphism is given by a direct association of each of the elements of D6 and H. So the association goes like this. 1 is sent to 1, r is sent to r square, r tilde is sent to r square, r tilde square is sent to r4, and so on. Each element is sent to the neighboring element in H. So phi of r tilde would be equal to r square, and phi of S tilde would be equal to S. And since R and S generate the entire sets, then we can just be satisfied with this definition. And this is injective and surjective, therefore it is an isomorphism. So even though D6 is not a subgroup of D12, it is isomorphic to a subgroup H of D12. So it has the same structure of a subgroup of D12. It is not itself a subgroup, however, it has the same structure. And in algebra, having the same structure is just as important as being equal, because isomorphisms in algebra means that we only care about the structure of the group. So it's just a matter of labeling, changing the labels of the set from D6 to H. So in conclusion, this result is equally as important as saying that D6 is a subgroup of D12, even though it is not. Okay, now we have seen two examples of dihedral groups which are not subgroups of another dihedral group. But what about subsets which are actually subgroups of the dihedral group? So if you take D8, for example, so let me erase this real quick, and D8 would be the symmetries of a square. So either the identity symmetry, a rotation, a double rotation, a triple rotation, a reflection followed by a rotation, reflection followed by rotation square, or rotation cubed. These are all the symmetries in D8. So we have that if we choose the elements 1, R square, S, and SR square, and put them in a set like this, we find that this subset of D8 is a subgroup. This is because it is not empty, it is closed with respect to the operation, which is a symmetry composition, and it is closed with respect to inverse because each element, for example, R square has an inverse. R square, its inverse is R squared, and it's also inside the subset. SR square has an inverse, which is SR squared. S has an inverse, which is S, and they all lie inside the subset. So this, in fact, is a subgroup of D8. The same can be said for 1, R square, SR, and SR cubed. This is another subgroup of D8. And this terminates the examples after following the definition of a subgroup. Having the definition of a subgroup is well and good, but it is tiresome to keep using the definition to verify that a given subset is in fact a subgroup. So what do we do? Well, there is a criteria, a proposition that says we can use a little amount of work for the same reward. So the work to be done will be explained in this proposition. Let G be a group, H a subset of G. Then H is a subgroup of G if and only if, so a double implication, if and only if H is a non-empty set, and if H1 and H2 are two elements in H, then H1 times H2 inverse is also an element in H. So by just proving these two statements, we have successfully proved that H is a subgroup of G, and moreover, if H is a subgroup of G, then we can deduce that we have these two properties. Moreover, if H is a finite set, it suffices to verify that if H1 and H2 are in H, then we don't even need to check the inverse. We can just check H1 times H2 is in H. Let's get to the proof of this very important proposition now. Okay, let's get down to the proof of this now. The proof will contain two parts. Will contain the forward direction and the backwards direction. In the forward direction, we will assume that H is a subgroup of G. So we will assume these three properties that we've discussed. And we're trying to prove these two properties on the right. So to prove the first property, notice that we've already assumed that H is non-empty. So by default, it's automatically proven. To prove the second property, we need to see that if H1 and H2 are an H, then H1, H2 inverse is an H. So if H2 in particular is an H, then by this property, we know that H2 inverse is an H. So now we have access to H2 inverse being an H. Moreover, if H1 is an H, so now we have both that if H1 and H2 an H, then by this property, we have that H1 times H2 inverse is in H. Therefore, completing the forward direction of the proof. Let us now prove the opposite direction. We have that H is non-empty, and we have that for all H1, H2, and H, H1, H2 inverse is an H. So we want to prove these three properties here. The first property, again, is very clear, so it is proven. We will start by proving the third property, and then we will prove the second property. So the third property has that H inverse is an H for any H. So if H is an H, then since we know that 1 is an H, we can use this property where 1 is here and H is there to say that 1 times H inverse is an H. But 1 times H inverse is equal to H inverse. So essentially we said that H inverse is an H, and we completed this part. So now we only have this part left to take care of. So writing it properly here, we have that H inverse is an H. And now for the second part, we have that if H2 is an H, then by this part that we've already proven now, we can say that H2 inverse is an H. And we're going to do a neat trick here. Look at this neat trick. What we're going to do is we're going to take the inverse of the inverse. So we're going to replace H2 by H2 inverse. And the inverse will take care of the inverse of H2. So if H1 is an H, then by setting here H1 by H1 and H2 by H2 inverse, we would have H1 times H2 inverse, inverse. And the reason we can do that is because we just proven that H2 inverse is an element in H. So in particular, we can use it in our supposed property here. So H1 times H2 inverse, inverse, which is equal to H1, H2. This element is an H, so that means this element is an H as well. And therefore, we have proven this third and last property. So proving the backwards direction and that H is a subgroup of G. So not only is this condition sufficient to prove that a given subset is a subgroup of G, but it is also a necessary condition that if H is a subgroup of G, then necessarily we have this property. Now we will see that if H is a finite subset, it suffices to only verify that if H1 and H2 are two elements in H, then H1 times H2 is in H, and we don't need to even look at the inverses. So the reason this is true is because since H is a finite subset, we have H, H squared, H cubed, H to the 4. Every time you multiply H, you end up with a different element. But since H is a finite subset, eventually you'll have to return back to the identity element because it can't keep going on forever. So the order of h is some integer L, and it's not infinite. Since the order is equal to L, that means by definition of order, h to the L is equal to the identity. Now we will use a neat trick to figure out what the inverse of h is in this case. We will separate h to the L into h to the L minus 1 and h, and this equals 1. And now we can see that the inverse of h is h to the L minus 1 because their product gives the identity element. So this means that the inverse of h is equal to h to the L minus 1. But h to the L minus 1 is an element in h because h as a subgroup is closed under operations. So if we know that it's closed under operations, then the inverse, which is equal to that, is also automatically inside h. Therefore, by default, inverses will also be inside h, and h is closed under inverses. So this is the nice property to have if h is a finite subset, thus terminating the proof of this proposition. Now that we have seen this nice property, it's time to put it to test. So I'm going to give you an example of a subgroup and an example of what is not a subgroup, and I'll explain why in both cases. So let G be an abelian group, commutative group, and let S be all the elements in G such that the element has a finite order. We have that S is a subgroup of G because, first of all, S is non-empty. This is always a condition that many people forget to verify when proving that it is a subgroup. So S is non-empty because the identity has order 1, a finite order, therefore making the identity a valid element in S. Secondly, we want to prove that for any G1, G2 in S, then G1, G2 inverse is also an element in S. So because G1, G2 are elements in S, they have finite orders. So we're going to let N1 be the order of G1 and N2 be the order of G2. Then we want to prove that the order of G1, G2 inverse is also finite. Well, the thing to do here is to use N1 and N2 somehow to get an order for G1, G2 inverse. And the suggestion that I'm going to use here is that it's N1 times N2, or at least less than N1 times N2. So G1, G2 inverse to the power N1, N2, literally speaking, repeat G1, G2 inverse N1, N2 times. So G1, G2 inverse times itself N1, N2 times. This is not a very nice expression right now. We want to simplify it, and we can because G is an abelian group. We can commute the elements in the expression to put all the G1s on the left and all the G2 inverse on the right. So we're going to have G1 to the power N1, N2 times G2 inverse to the power N1, N2. And now we want to use the fact that the orders of G1 and G2 are N1 and 2 respectively by saying, using the exponent laws, that this is equal to G1 N1 all to the power N2, G2 N2 all to the power minus N1. And now we know by definition that this here is equal to the identity, and this there is also equal to the identity, thus making all of this equal to the identity. Now, by a property that we've seen about orders in lesson 4, we know that if the element to a certain power gives the identity, then the order of that element divides that power. But if the order divides that power, then necessarily it has to be less than or equal to that power. It wouldn't make sense to be bigger than and to divide that power at the same time. So it is less than or equal to that power, but this is a number, a finite number. So necessarily this order here is also finite, therefore satisfying the condition that says that G1, G2 inverse is an element in S. Therefore, completing the verification of S being a subgroup of G using the proposition above. Now I'm going to be showing you an example of a subset that is not a subgroup, and I will prove it. If H is all the elements in the dihedral group D2n such that x squared is equal to the identity, this is not a subgroup of D2n for n bigger than 2 strictly, because we have that two elements S and SR are in fact elements in H because they satisfy the condition x squared equals 1. So S squared is in fact the identity. If you reflect the object twice, you get back the identity, and SR squared is equal to the identity as well. So we have that S and SR are in H, but we want to show that H is not a subgroup. So we want to show that S times SR is not in H. And this is easy to see because S times SR is equal to S squared R, which equals to just R. And R, the order of R, is equal to n. But n here is bigger than 2. And since the order is the smallest positive integer such that r to that integer gives the identity, and that integer is bigger than 2, then there is no way for r squared to be equal to the identity, since the order of r is bigger than 2. Therefore proving that S times SR is not an element in H, and therefore H is not a subgroup of G by, again, the proposition that we've seen earlier. Okay, let's now talk about the kernel and the image as subgroups of G and H respectively. We have a proposition here that says that if phi is a homomorphism going from G to H, then we have that the kernel of phi is a subgroup of G, and the image of phi is a subgroup of H. Moreover, a subset H of G is a subgroup if and only if there exists a homomorphism phi going from K to G such that the image of phi is equal to H. Now, let us see the proof of this proposition. First thing to prove is that the kernel of phi is a subgroup of G. To prove that, we need to use the proposition that we've already seen, where, first of all, we want to prove that ker phi is not empty. It's not empty. Why? Because the identity element of G is an element of ker phi. Since, remember, phi of G, phi of the identity of G is equal to the identity of H, which counts the identity of G as an element in ker phi. So it is not empty. Second of all, if G1 and G2 are elements in ker of phi, then by definition we have that phi of G1 is equal to the identity and phi of G2 is also equal to the identity. We need to prove that G1, G2 inverse is an element in ker phi. And to do that, we need to prove that phi of G1, G2 inverse is equal to the identity. And how do we do that? Well, we're going to use the property of the homomorphisms to say, okay, we can just separate the phi of G1, G2 inverse into phi of G1 times phi of G2 inverse. And we can use yet another property of homomorphisms to put the inverse outside the phi to say phi of G1 times phi of G2 with the inverse outside. And we know that phi of G1 is the identity, phi of G2 is the identity, so it's going to be identity times identity inverse, which is the identity. So we successfully proved that G1, G2 inverse is an element of Ker phi, thus completing the proof that the kernel of phi is a subgroup of G. Now, we will prove in a similar fashion that the image of phi is a subgroup of H. To do that, first of all, notice that image of phi is not empty because 1H is equal to phi of 1G. And phi of 1G is an element in the image of phi. So we have just found an element in the image, which is the image of the identity of G. So that means that the image of phi is not the empty set. There is at least one element in image of phi, which is the identity of H. Second of all, we have that if H1, H2 is in the image of phi, then by definition, we have that there exists some pre-images G1, G2 in G, such that phi of G1 is equal to H1 and phi of G2 is equal to H2. So we want to prove similarly as before that H1, H2 inverse is an element in the image of phi. So to do that, we need to prove that it is the image of some element in G. And what is this element in G? Well, we will find out now. So H1, H2 inverse is equal to phi of G1 times phi of G2 inverse, because we already have constructed it to be that way. And now we have that phi of G1 and phi of G2. We can combine them as before to say this is equal to phi of G1 times G2 inverse, and realize that G1 times G2 inverse is in fact an element in G, which makes this element in the image of phi. So because this element is in the image of phi, we have that all the conditions have been satisfied to say that the image of phi is a subgroup of H. Now, the last part of the proposition says that a subset H of G is a subgroup if and only if there exists a homomorphism such that the image of phi is H. We've already just proven this direction of the proposition, saying that if there exists a homomorphism with the image of P being equal to H, then H is a subgroup. We've proven that. And now we want to prove the opposite direction to say that, okay, what is this homomorphism that exists such that the image of phi is equal to H? And this homomorphism turns out to be a very natural homomorphism. So let H be a subgroup of G. Let that be a supposed property, and consider the homomorphism inclusion. So inclusion is nothing but the identity map, but into a set that is larger than the domain itself. So to explain what I mean by this, let phi be this inclusion map going from H itself to G. So clearly G is at least bigger, if not equal to H. And the map itself maps every element to itself. So it is the identity map just in a bigger set. So this is what we call an inclusion map. And we can see that it satisfies what we want here. There exists a homomorphism, and that the image of phi is equal to H, precisely because the map here is the identity. So it literally maps all of the elements to H to themselves in H. So the image of phi is exactly equal to H, thus completing the proof of this very important proposition about the kernel and the image. So we've just seen that the kernel and the image are both subgroups of their respective groups. But why is that important? How can that fact help us? Well, in this example here, we have that the special linear group SL and F, so recall this is the group of all matrices such that the determinant of the matrices is equal to 1. And 1 was the identity of the determinant homomorphism. So really what we're saying is all of the matrices such that if you apply the determinant on that matrix, you get back the identity. So if A is in SL and F, then that means that the determinant of A, so this can be considered as the phi, the homomorphism, is equal to the identity. So A would be inside the kernel of this phi being the determinant, so the kernel of the determinant. But we've just said that the kernel of the determinant is a subgroup of G, and G here is the general linear group, which is all the matrices of non-zero determinant. So really, when we're talking about the special linear group, we can consider it as the kernel of the determinant, and so it is a subgroup of the general linear group because precisely of the proposition that we've seen that said that the kernel of a homomorphism is a subgroup of G. So SL and F is a subgroup of GL and F precisely because SL and F is equal to the kernel of the homomorphism determinant. So without using any of the previously mentioned criteria to prove what a subgroup is, we have just proven that SL is a subgroup of GL. Let us use this same exact notion with AN and SN. So AN is the set of all the cycles that have even number of transpositions. In other words, it is the set of all the permutations such that the sign of that permutation is equal to 1, which is the identity in the multiplicative group C star. So using the same argument, we can say that AN, the alternating group, is equal to the kernel of the sign homomorphism. And again, the kernel of the homomorphism is a subgroup of G, which in this case, G is Sn. So this means that AN is a subgroup of Sn. So this is where it comes in handy. It's how to prove that certain groups are in fact subgroups of bigger groups using just the kernel of some homomorphism that starts at that ambient group. The last thing to cover in our lesson is that the intersection of subgroups is itself a subgroup, and this will be the proposition that I will prove now. Let G be a group and Hj over all the j's be a collection of subgroups of G. So the j here is the index of each Hj. Then the intersection of Hj, so this symbol here is the intersection of Hj as we run through the j's. The intersection of Hj here is a subgroup of G. And to prove that, we want to prove two things as usual. Prove that the intersection is non-empty. And this is true because each Hj is supposed to be a subgroup of G. So it's a subgroup of G. So there exists the identity in each Hj, the identity of G in each Hj for all J. So that means that if we take the intersection of all the Hj's, we will definitely have that the identity is inside the intersection since it is found in each of the individual subgroups. So therefore, this is proven. The second part of the proposition, the proof says that if we have h1 and h2 in the intersection of a j, for each j, we want to prove that h1, h2 inverse is in the intersection as well. So here we're going to be using the same argument we used in the first one to say that since h1 and h2 are in the intersection, then they are found in all of the edges. So h1 and h2 is an edge for all of the j's. So if they're there for all of the j's, so for all of the j's, we have that since H is a subgroup of G, no matter what J is, we have that H1, H2 inverse, by definition of subgroups, is a member of a J for all of the J's. So if it's on all of the edges, so it has to be in the intersection of all the edges. So this means that H1, H2 inverse is inside the intersection of edges for all J, thus completing the second and final part of the proof of the proposition. And with that, we have terminated our lesson. If you have enjoyed this, please like and subscribe, and I will be posting many more videos in group theory where we'll be discussing very interesting results that will come up later on. Have a nice day. Bye.